Okay, Chinta, it's all yours.
Hi guys. I'm sorry if I talk a little low. I've just been getting over a sinus infection, so if I start talking louder, I'll cough. So I hope everyone can hear me. So I'm going to talk about how I used BiogeoBest to basically answer a question for my PhD work. I worked on blindsnakes, and I wanted to figure out where the genera of blindsnakes that we have in India, where they came from. So before I start, from Praveen's talk, you know now that biogeography is the study of species at along a spatial and temporal axis. And to basically explore the biogeography of a group, we need two key pieces of information, which is the current distribution of the taxa in the landmass and the time of divergence between those taxa. And from a lot of studies in our lab and from other studies in India, we know that India's biota is composed of groups of diverse biogeographic origins. Some of them are ancient Gondwanan lineages which have persisted on our landmass, and we also have recently dispersed elements which have come in from, multiple landmasses from Africa and from Southeast Asia. We also have endemic radiations, so, within the Indian landmass. And a brief brief recap of India's geological history. So we know that, is it moving? Is it moving? It's not moving. Okay, it's supposed to be a video. But we know that, India was part of Gondwana land, and then about 160 million years, Gondwana split into East and West Gondwana. India was part of East Gondwana along with Madagascar, Australia and Antarctica, and West Gondwana was Africa and South America. Come on. Oh, never mind. Then India, Madagascar broke away from Australia, Antarctica, and finally, around 90 million years ago, India broke away from Madagascar and started drifting northwards towards Laurasia. So there's one theory that says that, this northward drift was basically India was all alone until it collided with with Laurasia. But there are other theories that say that during its northward drift, it could have made these little contacts with the northern tip of Africa, because Africa had also moved by then. And before it finally collided with Laurasia, it made like a glancing contact with Sumatra, or the landmass around Sumatra. So all these connections could have been times when taxa could have dispersed into India. And we kind of apply all these ideas into answering the question. So a brief about my model system. So blindsnakes belong to the infraorder Scolecophidia. It's one of the two infraorders within Serpentes. And they consist of some of the smallest known snakes. It's a paraphyletic infraorder, so there are basically two families and one superfamily. And this Alithnophidia is where all our typical snakes fall. And Scolecophidia consists of some of the smallest known snakes. The smallest is 10 centimeters. They grow up to around a foot. They're all fossorial. They have reduced eyes. So the scales cover their eyes, and they also have only rods in their eyes. They don't have cones. And their jaws are also reduced. So from this you can see that, the bones are all fused together. And basically they eat larvae of ants and termites. So they don't really need huge jaws. They're also non-venomous. Most of them don't have teeth or have like 1 or 2 teeth in the lower jaw. But that generally sums up, the characteristic of this infraorder. And blind snakes fall within the superfamily Tiflopoidia. This superfamily consists of 3 families. Geropelidae, which is distributed in southern Western Ghats, Sri Lanka, Northeast India, and then some regions of Southeast India. They're mostly wet adapted snakes. Tiflopidae, which is endemic to Madagascar, and Tiflopidae, which is the largest group of blind snakes. They're distributed across most of the continents except Antarctica. And within India, we have 4 genera belonging to 2 families. We have Geropilus, which belongs to the family Geropilidae. And we have 3 other genera from Tiflopidae, which are Indotyphlops, Agarophis, and Grypotyphlops. Agarophis is currently found only in the northeast regions of India, so it doesn't really fall in the Indian biogeographic region. And Indotyphlops is found across most of India. I'll come to Indotyphlops later. And Grypotyphlops is endemic to peninsular India. So when I started off my work, this is what we knew about blind snakes from India. And there were very few studies, one of which had listed 17 species from India. But we didn't know whether some of these were synonyms, some of these hadn't been, found again after the first description. So we had very little to go on. So I decided to focus on only the genera because I didn't know much about the species. They're also very difficult to tell apart. So I didn't know what species I actually had in my collection and all of that. So we decided to basically focus on the 4 genera and look at, where they fall in the global phylogeny and their biogeographic history. So I had 2 objectives. The first one, of course, was to build a phylogeny and see where the Indian genera fall in the global phylogeny. Thankfully, there was a study in 2010 which had sort of sampled all the other blind snakes from across the world, or most of them. And so I wanted to plug in the Indian genera in there and see what their relationships are. And from there, I wanted to move on to exploring the biogeographic origins of these genera. So until we started our study, a lot of the studies till then classified these blind snakes based on morphology. And there was the first phylogenetic study was in 2010, and there were other studies which later built on this study, but most of them were missing the Indian genera. And for the 2 genera that were there in the phylogeny, the samples didn't come from India. So we wanted to, first plug those gaps and sort of complete the phylogeny. So I collected samples for the 4 genera and carried out a genus level identification. Some of the species were also identified, carried out DNA extraction and PCR. I used 5 nuclear markers. These were the markers that the other studies had used, so I could use it in that phylogeny. I'm guessing you guys are all familiar with all these tools now because you've covered it in the practicals. So found out the best fitting models, built ML and Bayesian trees. What I found was, it's a really large phylogeny, so I'm just going to zoom in to the relevant parts. So what I found was that Geropilus from India was sister to all the other Tiflopoids. So it was the oldest, it was sister to all the other Tiflopoids, so Grypotyphlops is a monotypic genus. There's only 1 species in that genus, and that's Grypotyphlops acutus, and it's endemic to India. But based on its morphology, it has been classified in the family Afrotyphlopinae so far, because it has this shield-like rostral scale. And that character is found in all the African blind snakes. So our results showed that the molecular data also corroborates the same classification, and it is actually sister to the African genera. We had Indotyphlops, where we actually found that Indotyphlops is not monophyletic. We have Indotyphlops brahminus and parmesis and a whole bunch of species that form one clade. And then there is another species called Indotyphlops porrectus, which was actually sister to all the Southeast Asian Tiflopids, all the Southeast Asian blind snakes. So the earlier classification was based on morphology, and from the molecular data now we know that this is going to be a new genus. It's not actually Indotyphlops. But again, they look very similar. Their morphology is very conserved because they are fossorial animals, and it's very difficult to tell apart. Yeah. So, and of course, we also had Argyrophis, which was, our sample was falling within the clade that was from Southeast Asia. But then that's no surprise because our sample was also from Northeast India. But yeah, that was, so we managed to complete the phylogeny. So then we decided to move on to the biogeography analysis. And like Praveen mentioned, you need to have a time tree, to understand the divergence times of these groups to understand their biogeography. So I carried out divergence time estimation in bees, and I used 9 fossils to calibrate the tree. And we did ancestral range estimation using BiogeoBase. But using BiogeoBase, I carried out something called model fitting, which I'll explain in the subsequent slides. So the 9 fossils I used are right there, and there aren't any usable blind snake fossils, so I actually had to use fossils within Tiflopoidia, and I added a whole bunch of lizard samples as outgroups, lizard species, and I used fossils from the lizards to calibrate the tree. Okay, so before we get into BiogeoBase, I used a model called DEC plus J, but BiogeoBase also allows you to allows a whole bunch of other models. So DIVA, like Praveen mentioned, DEC, and something called Bay Area. You can implement all these 3 models in BiogeoBase. You can also implement DIVA plus J, DEC plus J, and Bay Area plus J, which is basically these models, but with a jump parameter added to it. And I chose DEC because I from the dated tree, I knew that my group was really old. It's about 100 million years old. So, I wanted to have all the parameters of dispersal, extinction, sympatry, vicariance, all of those to be used in my analysis. So I used DEC, but from that 2010 study, it was hypothesized that, blind snakes might look dispersal limited because they're really small and fossorial, but it's possible that they actually carried out oceanic dispersal. They might have sort of floated on this rotting log of wood, which sort of, drifted towards another landmass at a time when currents were really strong in one direction. And if these rotting logs sort of had termites or whatever, they could have survived the trip. And that's how they're supposed to have gotten to Australia and to South America from Africa. So these are really large, long distance dispersals. And uncharacteristic of such a small animal, they can carry out long distance dispersals. So I decided to use the plus J model to allow for jump dispersal. And I used, so now I'll come to the model fitting part. So by model fitting, I don't mean that I use these 3 models. So or I should call it something like hypothesis testing. But I came up with these 3 hypotheses. And one was the vicariance and dispersal model. In this, I wanted to test whether vicariance or dispersal or both were, played a role in the distribution of blind snakes right now. And so for this model, I constrained my analysis, and I'll explain how I do that here as well as in the practicals. And so I constrained my analysis such that before 90 million years, as in, when India and Madagascar were together, these lineages, so any lineage that is older than 90 million years could have come about because of vicariance. But any lineages younger than 90 million years, that is when India was sort of drifting by itself, could have come about only because of dispersal. Because, it's this moving landmass and lineages should have had to disperse into India for it to be found there. Like what I did is, 160 to 120 million years and 120 to 90 million years, between these time periods, I allowed for bidirectional dispersal, which is seen by the double-headed arrow. So between the land masses close to India, I allowed for direct dispersal in both directions. But after 90 million years, I allowed for dispersal only into India and not out of. To account for, my theory that younger lineages that are found in India have all dispersed into India. I know it sounds a little complicated right now, but when you finally get around to looking at the matrices for biogeobears, it'll make a little more sense. So that was my first model. And for the second model, I hypothesized that the whole group had an African origin, and all the blind snakes around the world right now had dispersed out of Africa into every landmass. And so I constrained for unidirectional dispersal out of Africa for all time periods. Sorry. Yeah, so here, regardless of the time period of the analysis, I did not allow for dispersal into Africa, so only out of Africa into every landmass. And model 3 was the null model where there were no constraints. I decided my biogeographic areas mostly based on the Gondwanan fragments because I am testing for Vicariance as well. I also use Wallace and Lydecker's line as barriers. So I had this one group of islands called Wallacea. Papua New Guinea was a different biogeographic region because, studies have shown that they have their faunal, the biota is basically of diverse origins. So it's not the same as the Australian biota. So I had PNG as a different region, Philippines as a different region because it again has its own biogeographic history. But the rest of the landmasses were, the Gondwanan fragments. I also carried out time stratified analysis. So here, this is where Lagrange sort of fails because Lagrange does allow for time stratified analysis, but for a landmass like India, which has also moved through time, you can't actually code the area adjacencies for the landmasses for different time periods. And this is where biogeobears gives you an advantage because, so in Lagrange, I think you code for area adjacency for the same for the entire, time period of your analysis. But biogeobears, you can break it up into whatever number of time periods you want, and then you can code the dispersals and the adjacencies differently for each time period. For most other groups, not in India, it wouldn't really matter much. But India has moved a lot over geological time, so that's really crucial to be able to code the adjacencies differently. So I broke it up into 6 time periods. So 160 to 120 million years was when India was part of West Gondwana and it was very close to Africa. 120 to 90 million years was when India and Madagascar broke away from Australia and Antarctica. 90 to 80 was when India was separating from Madagascar, and 80 to 55, basically 80 to 35 is when India was moving northward, but I broke it up into 2 because between 80 and 55 India was closer to Africa, and 55 to 35 India was closer to Asia. So I wanted to be able to code my dispersals differently for those time periods, so I broke it up into further 2. And 35 to present was, after the hard collision. Okay, so what I meant about being able to code area adjacencies differently is, so these are, for the biogeographic areas, and the matrices go from, column to row. And so before 120 million years, I coded Africa and India as adjacent. And this has got to be a symmetric matrix. You can't make a non-symmetric matrix for area adjacency. So Africa to India was 1 and India to Africa was 1 because India and Africa were close together. They were adjacent. But between 55 and 35, India had moved quite far away from Africa. So I coded that as a 0. And India was closer to Asia then. So India to Asia is 1. And Asia to India is also 1. Yeah? So this is how the area adjacency matrices are coded. And you can do it for every time period differently. Yeah. So remember the 3 models that I spoke about that I wanted to test. Those models, you can constrain your dispersal multipliers to implement those models. And I'll show you how I constrain for model 1. Which is the Vicariance and Dispersal model. Here I am assuming that any lineage older than 90 million years came about because of Vicariance, and all the lineages younger than 90 million years that are found in India were because of Dispersal. Okay, so we're looking at the time period 160 to 120 million years. India was close to Madagascar and Africa at that time. This is a time period that sort of indicates the east-west Gondwana separation. And so you can see that this is a bidirectional arrow, and the dispersal probability is 0.75. Now it's 0.75 because East and West Gondwana had already separated at that time. So there is a sort of barrier. The ocean is a barrier, but they're close enough that the dispersal isn't really low. So I considered land connections as a probability of 1. And anything that's not connected by land decreases in my analysis increments of 0.25, but you can choose whatever. You can code it as whatever because the dispersal multipliers are all relative. So it doesn't matter if it's 0.8 and 0.2 or 0.75 and 0.25 as long as one is substantially larger than the other. So yeah, so between 160 and 120 million years, I coded the dispersal as, I allowed the dispersals to be both ways. So from Africa to India and from India to Africa. Sorry. Yeah, also, sorry, I didn't highlight it in a box, but you can see that India to Madagascar is 1. And Madagascar to India is 1 because India and Madagascar are connected at that time. So yeah, so the second time period is 90 to 80 million years when India had separated from Madagascar or had begun separation from Madagascar, and now we are constraining for unidirectional dispersal. So it's a single-headed arrow, and you can see that Africa to India is 0.5. It's 0.5 because it's not here anymore, so it's not 0.75. But India to Africa is a lot lower. Another point before you guys get confused, these are supposed to be zeros, but Biogeobase throws an error. If it's 0, it will say that your analysis is like too tightly constrained and it'll keep crashing. So they recommend that you put a very low value, and that's why these are all 0.01. It doesn't mean that there's dispersal happening here. It's basically 0 dispersal. So, so because I wanted to code it for unidirectional, I gave it a very low dispersal value. So dispersal is higher in one direction. Yeah, and then we come to the 55 to 35 million year time period where India was closer to Asia and further away from Africa. That doesn't mean that dispersal can't happen from Africa, but it will be, the probability will be lower from dispersal, compared to the dispersal from Asia to India. And that's why the thicker arrow from Asia into India and the thinner blue arrow for Africa, which corresponds to the similar colored squares. So you can see that Africa to India is 0.25 now. India to Africa is still remains low, but Asia to India is 0.75 now, and India to Asia is low still. So we are still coding for dispersal only in one direction. Okay, so this is an example of how I coded one of the models. All right. So anyway, I ran BioGeoBase for the 3 models, and I calculated the Akaiki weights for the 3 models, and so it'll give you a likelihood value because BioGeoBase runs on an ML framework. And well, the results showed that M1, which is the Vicariance and Dispersal model, was the best model. But I'm going to go over the results of the 3 models and also explain why we didn't just go by the stats. The results also make more sense because of this for the first model. So from model 1, we saw that, I also used an outgroup or a sister group, which is thread snakes. And it showed that, Tiflopoidia, which is the superfamily, and Leptotiflopidae, they had a Gondwanan origin because the ancestral area was Africa, India, Madagascar. So the ancestor was found in Gondwana, and when East and West Africa broke away from each other, which is the gray, which is IM, that is for East Gondwana, and this is for West Gondwana, which is Africa here. So the vicariant event of East and West Gondwana separating was what caused the divergence between leptotiflopids and tiflopids. And then, so this ancestral area you can see is India, Madagascar, and that broke away to give Geropilus, which is found in India, which is the orangish yellow here, and the rest of the tiflopids, which were found in Madagascar. So this is a very clear example of vicariance because the ancestral area was a combination of the two, and then there's one lineage found on one of the land masses, and the other lineage, or the ancestral of the other lineage, was found in the other landmass. And the time period also, it's 109 million years, but the confidence intervals sort of overlap the time around which the two landmasses started splitting. So, like Praveen was mentioning, the time and the areas make sense. So this divergence we attributed to vicariance. But for the other lineages, it shows a very clear dispersal from another landmass. So Grypotiflops, as I mentioned, was classified in the family Afrotiflopinae based on morphology and molecular data, and it shows that it actually dispersed from Africa around 58 million years. So the ancestral area for that node is very clearly Africa, not a combination of India and Africa. And it shows a jump dispersal from Africa to India. And so around 58 million years, India was sort of drifting northward. It was sort of in between Africa and Asia. So it looks like Grypotiflops was a result of a pretty long jump dispersal. And for the rest of the genera also, it shows jump dispersal. So Indotiflops correctus, which is now going to be called Pseudo-Indotiflops correctus, was again a jump dispersal around 63 million years from Asia into India. And then there was another jump dispersal from Asia into India around 55 million years, which led to the Indotiflops lineage in India. So there has been one vicariance and 3 dispersals explaining the distribution of blind snakes in India. Argyrophis is, well, still, we coded it as Southeast Asia because the northeast region of India is not biogeographically India, but there are reports of Argyrophis from Odisha. So if we manage to, if somebody manages to find those, plug it in this, we might know about the dispersal of Argyrophis into India, which is probably going to be very recent because the age of that group is 4 million years. So it's going to be a very recent dispersal over land into India. So that was model 1, which was the first model, and the story very clearly makes sense because the dates match and the landmass, the geological history matches. It's a very neat pattern. But you can't rule out other possibilities, which is why we tested the other models. And this is the one where we tested for Africa as an ancestor. And we do see this pattern in Ranidae family of frogs. So we wanted to test it out for blind snakes as well. So here, basically the results show that, the whole group has an African origin, and it's all dispersals from Africa into all the other land masses. All the, ancestral areas are Africa. And, while it's not impossible that this could have happened, if Africa was the ancestor, then we expect Africa to have an old lineage like Geropilus or Xenotyphlops on it, because obviously nothing has wiped out blind snakes from these land masses. So the absence of a really old lineage in the ancestral area sort of goes against that theory that Africa was the ancestral area. And the null model, the null model doesn't make sense at all, because apart from the low likelihood values, it basically, so this is one of the problems with BioGeoBase, because it allows for jump dispersal, it sort of goes crazy with it, and it invokes jump dispersal like randomly. And like what it's done here is, it has invoked a jump dispersal for Grypotyphlops. This is the one that came in from Africa. Before 58 million years, from Africa to India, and then from India to Africa, it jumped back. Like from India, it jumped back to Africa. And I'm just thinking, these are not animals that can fly long distance or swim in water or anything. They basically, like one chance log, they jumped on it and they came into the other landmass. How often is it going to happen that it can just keep jumping between land masses that are this far away? So, parsimoniously, it doesn't make sense, right? And the null model does it for like most nodes. So again, from Asia to India, and then India to Asia. This is before India and Asia were connected. And it also does it in the sister group, and this is the most ridiculous. Africa to South America, and then from South America back to Africa. This is not when they are, together as West Gondwana, West Gondwana. This is when they're like really far apart. So these line snakes caught a lucky boat once, but it's not gonna keep happening. They can't keep going back and forth. So that's why the null model doesn't make sense. And unfortunately, a lot of the earlier studies that used BioGeoBase sort of used it in the default settings. And some of the results actually show this, that there are they've actually inferred that there was an earlier dispersal and then a back dispersal. So you have to learn how to use this tool. You have to really figure out the intricacies of how to code the matrix, and you can answer very interesting questions with this. But anyway, I had to throw the null model in there because you don't want people to say, but how do you know you got this result, because you didn't really constrain your data to fit what you want. So that's what happens when you use it in the default way that BioGeoBase is being used. So those were the three models. So to conclude, we found out that Vicariance and Dispersal have both played a role in the diversity and distribution of blind snakes in India. Geropilus is an old lineage, and it is explained by the Gondwana breakup scenario. Grypotyphlops is a pre-collision dispersal, so jump dispersal from Africa. Indotyphlops is again a pre-collision dispersal with Porrectus group jumping in from Africa, from Asia before the other Indotyphlops group. And Argyrophis, if confirmed from the Indian sub-region, will be an example of post-collision dispersal into India. Okay, I'm done. So if you have any questions about the blind snake work, please feel free to ask. If you have questions about biogeobears, we'll cover it in the practicals now.
Yeah, I missed the first part where they mentioned sympatric subset and narrow. What, like, I missed that. Like, how do you differentiate sympatric subset and narrow?
Before I started?
Before you started that model thing.
Yeah. I'll go back. Did I say that or did Praveen say that in his talk?
It's there.
Okay. Going back. Oh, this one.
Yeah.
Oh, yeah. So this is from Matske's paper where Nick Matske, who developed biogeobears. This table is right from his paper. Basically, it shows you what the different models in biogeobears can do and, how to pick the model you want. So I didn't pick BIVA because it doesn't allow for sympatry. It doesn't allow for sympatry. It only allows for vicariance, 2 types of vicariance, and these 3: dispersal, extinction, and narrow sympatry. Although, because by blind snakes, sympatry really doesn't play a role in it. Even if I had used DIVA, I might have gotten the same results. I used DEC because dispersal, so blind snakes are they're 100 million years old. So it's an old enough group that, extinction, dispersal, all of these can play a role in their distribution. I was obviously testing for vicariance, which is why I needed a model which would allow for that, which is why I didn't use Bay Area. So, I've included the papers in the reading material for the practicals, so you can read it a little more in detail. So basically what Biogeobears does is it allows you to test out all these 3 models, plus all these 3 models plus J. So you can basically run 6 models in Biogeobears. I'm going to be covering that in the practicals as well. But there's a critique on Biogeobears that reviewers really like to throw at you if you have used Biogeobears in a paper, which is that so when Matske proposed Biogeobears, the way he said you could use it is run all these 3 models and all the J models on your data set and then pick the best model based on the log likelihood or the AIC value. And the criticism says that it's wrong to do that because the analysis always gives the J parameter a higher weightage than the other parameters. And if you use something like, so if you're comparing DEC and DEC plus J, J has a higher weightage, it assigns a higher weightage, then it's obviously going to be better, right? And how can you compare 2 models which don't have the same number of parameters? Like DEC is 3 parameters, but if you add plus J, it's 1 more. So obviously, 1 more and not equally weighted. So if you compare just the AIC values, you're always going to pick the values are always going to pick J as the better model. And that is wrong. We agree. So the way to use Biogeobears is not to actually blindly run all these 3 models on your data set. You first understand the group. So, if it's a very young group and, you can use any of the other models, or if vicariance doesn't come into play in your group, then, don't use one that allows for vicariance. You can use another model. But understand which model out of the 3 to use based on your data set and your group, and don't use DEC and DEC plus J and say DEC plus J is better. Use the plus J model only if you think your taxa actually carries out jump dispersal. So what I did was I only used the DEC plus J model. I didn't use any of the other models, but I basically had these 3 hypotheses which I compared using the AIC values. So here my model, the Biogeobears model, is the same. I'm comparing the same number of parameters. I'm just changing the scenario by tweaking my dispersal multipliers. So in the end, when I get a log likelihood value, they are based on the same 4 parameters for the 3 scenarios that I have created. And yeah, so and I've included the critique as well in the reading materials, so you're free to look at all of that. And this work was published early this year, so that paper is also up, and you can have a look at that. The matrices are also included in the supplementary materials, so if you want to really have a detailed look at it, it's all there. Yeah. Any other questions? Shall we move to the practicals then? Oh, T. Okay. All of it sounds a little complicated when I explain it, because it's all, for you guys, you're not familiar with the work, but when you start using it on your own data sets, it'll make a lot more sense. So today for the practical, I'm going to cover the example data set from the paper because it's accessible to everybody. But, try it out on your own data sets, and then you'll understand how to tweak it for what you need it to do.
You have not done optimizations for these substitution matrices, right? Your distance matrices?
No.
So would that significantly affect the likelihood? Because for some combinations you might get a very good likelihood value.
It will, but then if you got to use the same set of values
Across.
for the 3 models, and in the end, in the Akaiki weight, it will sort of all level up, right?
Normalize it.
Yeah.
Cool.
Yeah.
Fancy work. I have attended your talk previously, but I never spoke to you because it was online, and I was like,
I know. Honestly, I was glad nobody spoke to me. I was so tired of it. I'm like, I just want to be done.
but fancy. And like these guys have no other means of dispersal other than just the log scenario, possibly.
Yeah, I think all the dispersals have been passive.
Dude, balloon spiders में क्या सीन होगा ना अगर ऐसा चेक किया तो?
किसमें?
Balloon spiders.
Spider, yeah.
Crazy. That would be one interesting taxa to look at.
Nick Matske?
Yeah, Nick Matske is publishing a paper. It is already in preprint. It has not come out yet.
Is it the star wala paper?
Star.
It is
Oh, okay, go on.
So here he